Now we'll start the section that deals with stoichiometric calculations for chemical reactions, and we begin this section by talking about balancing chemical reactions. Stoichiometric calculations are super important in chemistry because they allow us to predict how much product might be made when you do a chemical reaction. Now, in order to do a stoichiometric calculation, you must have a chemical reaction written out, and it also has to be balanced for mass. This is crucial because matter cannot be created or destroyed when you do a chemical reaction. And another way of saying that is when you write a reaction, it has to be balanced. You're going to have the same mass on the reactant side of the equation as you have on the product side of the equation. Let's get a little bit of practice with balancing equations. Here we're told that aluminum metal reacts with oxygen gas to produce aluminum oxide. We'll start by writing an unbalanced reaction We'll start by writing the unbalanced reaction. So we're going to convert the words given in the problem into some sort of symbolism here. So we start with aluminum metal, so that's Al solid, reacts with oxygen gas. Remember, oxygen is a diatomic molecule, so O2 gas goes to make aluminum oxide. Be careful when you convert the words into a formula here. You've got to make sure that you know the ion charges. Aluminum is Al3+, and oxide is O2-. So the formula for aluminum oxide is Al2O3. All right, so our reactants here are aluminum and oxygen. They combine to form our product, Al2O3. Now we have to balance this equation because when we take a look at it, we recognize that we don't have the same number of each type of atom on both sides. We have 1 aluminum on the left and 2 on the right. That's not okay. You can't just create bonus aluminum atoms out of nowhere. This reaction has to be balanced for mass. And so to do that, we're going to start with the most complex molecule, which is, in this case, Al2O3. Now from there, we're going to work on balancing everything except for oxygen and hydrogen. We're going to deal with those last because they're a little bit trickier to deal with in a lot of problems. So we'll begin by looking at the aluminum from Al2O3. We see here that there are 2 Als, and on the left-hand side of the equation, there's only 1. And so to have an equal number of aluminums on both sides, we'll need to multiply the aluminum by 2. So 2 aluminums plus O2 goes to Al2O3. And we put this coefficient of 2 in front of aluminum to basically multiply it by 2, but also to say it's 2 aluminum atoms. It's crucial that when you balance equations, you're multiplying by coefficients and not changing subscripts. Because if you change subscripts, that kind of changes the properties of the substance you're dealing with. You can't write it as Al subscript 2 because aluminum is not a diatomic element. It's monatomic. And so you have to keep it as individual aluminum atoms and then just say you have 2 of them. Now that we've balanced the aluminum, we'll come back to the Al2O3 and recognize that the only element left to deal with is oxygen, so now we have to work with this. We have 3 oxygens on the right-hand side of the equation, and there's only 2 on the left-hand side of the equation. You can't just change the subscript. We have to multiply it by a coefficient such that we get 3 oxygens on this side of the equation. And the coefficient that will give you 3 will be 3/2, because 3/2 times 2 equals 3, and then you'll have 3 oxygens on both sides. So now 2 Al solid plus 3/2 O2 goes to Al2O3. And now this equation is balanced. We have 2 aluminums on the right and left side, and we have, 3/2 times 2 again is 3 oxygen atoms on the left side, and we have 3 oxygen atoms on the right side. So this is balanced. But there's a problem. We don't want to use fractional coefficients. So one more thing that we'll need to do is convert all of the coefficients into whole numbers. Let's think about how that would be done. To get a whole number, what we can do is multiply everything in this reaction by 2. Multiplying by 2 will allow you to cancel out the halves that are here and get you to a whole number. But you can't just multiply the O2 by 2, because if you do that, the reaction is no longer balanced. Instead, you have to multiply every single thing in the equation by 2, because if you apply the same change to everything, that will keep the reaction balanced. So everything here gets multiplied by 2 so that we generate whole number coefficients. Therefore, we will end up with 4Al plus 3O2 going to 2Al2O3. And this equation is balanced. We could double check it to make sure that we have an equal number of each atom on both sides. And what we'll see is that on the left side, there are 4 aluminum atoms. On the right-hand side, we have 2 times 2 gives you 4 aluminum atoms. We have 3 times 2 gives you 6 oxygens. And on the right-hand side, you have 2 times 3 gives you 6 oxygens. And so this is balanced. Now, looking at this balanced equation, it's really important for us to also think about how we can convert the symbolism that's shown here into words. So we're going to ascribe physical meaning to what this balanced equation is telling us. That is so important, not just in a problem like this, but really in any chemistry problem. You want to try to give physical meaning to things so that they don't seem so abstract. That's going to be really helpful when we go on to discussing how we can use a reaction to do a stoichiometry problem. So in words, what this reaction tells us can be one of 2 things. One way you can look at it is to say that in this reaction, 4 atoms of aluminum react with 3 oxygen molecules to produce 2 molecules of aluminum oxide. Alternatively, we could use other words that represent numbers. So you could also say that 4 dozen aluminum atoms react with 3 dozen oxygen molecules to give you 2 dozen aluminum oxides. Or you could also use another word that represents a number, and that word is mole. So you can say that 4 moles of aluminum would react with 3 moles of oxygen to produce 2 moles of aluminum oxide. And that's going to allow us to generate another type of a mole ratio, one that can be used to convert moles of maybe a reactant into moles of a product, saying that for every 4 moles of aluminum you have, you can make 2 moles of aluminum oxide. This is where we're going to start talking about how stoichiometry can help us to predict how much product you can make given a certain amount of reactant. And that's what we're going to get into more detail about as we continue on in this chapter and talk about actual stoichiometric calculations. But before we do that, we're going to get a little bit more practice with balancing. And I want you to take a look at this reaction between calcium phosphate and sulfuric acid to make calcium sulfate and phosphoric acid. I want you to balance this equation and determine the coefficient in front of sulfuric acid when the equation is balanced using smallest whole number coefficients. And I will say before you begin on this, there is a really quick trick that you can use to answer it, so you can balance it in like less than 30 seconds. Hopefully you're able to see the trick and you can balance it quickly, but if you're not, don't worry about it, because on the other side of the question, we'll talk about how you can do this really, really quickly. All right, having given you some time to work through this, let's talk about how to solve the problem. So the quick trick to answer this is to recognize that in this problem, all of the substances that we have contain stable polyatomic ions, and those kind of exist together as a stable group. And so you can balance those groups of atoms together. So you can balance phosphate groups, right? You don't have to balance phosphorus atoms and oxygen atoms. Balance the polyatomic ions as a group. All right, with that in mind, we're going to start with the most complex molecule first, which is the calcium phosphate. When we come over to the right-hand side of the equation, we only have one phosphate ion in H3PO4. So we're going to multiply phosphoric acid by 2. Now I have 2 times 3 is 6 H plus ions. So that means I have to have 6 H plus ions on the left-hand side of the equation. I'll come over to H2SO4, therefore, and multiply that by 3. So 3 times 2 gives me 6 H pluses. Now by making that change, I've now changed how many sulfates there are. So now I have 3 sulfate ions on the left-hand side of the equation. That means I have to have 3 sulfate ions on the right-hand side of the equation. So when I come over to the right-hand side of the equation and look at CaSO4, I've got to multiply by 3 to give me 3 sulfate ions. Now I have 3 calciums, and so I have to have 3 calciums on the left-hand side of the equation, and I already do. So I've come back to where I started this problem. That means that everything's probably balanced. And you can check it, you could add everything up and see that it is all balanced. And so what we end up finding here is that the coefficient in front of H2SO4 is 3. That's our answer here. And you can balance this equation very quickly when you have polyatomic ions, provided that you keep the ions together as groups. If you try to break them up into all the atoms, it's going to take you forever to balance. All right, next up, we're going to look at doing stoichiometric calculations. So we're going to use balanced equations to make predictions of how much product can be formed in a reaction.